Okay, let's take a moment and talk about pH. Before we really get into pH and calculating pH, I want you to think about something and realize something from our self-ionization of water videos. This is some good information for you to have in the back of your mind. Any aqueous solution, salts, acids, bases, but any aqueous solution has a hydronium ion concentration and a hydroxide ion concentration. So any aqueous solution has a hydronium ion concentration and a hydroxide ion concentration. And don't forget, Kw equals the concentration of hydronium times concentration of hydroxide. So tuck that away in your memories. Use it on a rainy day or snowy day, because that's good information to keep in mind. Any aqueous solution, acid, base, salt, if it's in water, it's going to have a hydronium ion concentration and a hydroxide ion concentration. So, speaking of hydronium ion concentrations, pH. So, we have learned that whether or not something's acidic, basic, or neutral, it all depends on the hydronium ion concentration. Okay? So based on that, we can determine if something's acidic, basic, or neutral. If it's acidic, the hydronium ion concentration is going to be greater than 10 to the negative 7th. If it's a base, it's going to be basic. The hydronium ion concentration less than 10 to the negative 7th. And if it's neutral, hydronium ion concentration is going to be equal to 10 to the negative 7th. Okay, so what does all of this have to do with pH? Well, pH you can think of as power of hydronium ion concentration. So pH is the power of that concentration. pH is a logarithmic function, and in the appendix in your book you can look up more information about logarithms, but hopefully in math class you've learned plenty. So the formula for pH equals the negative log of the hydronium ion concentration. Sounds like hydronium ion concentration is a little bit important. Okay, let's take a look at this image. I know the words aren't clear, but the middle part isn't what's important. The important part is the hydrogen ion concentration at the top and the pH at the bottom. So let's see how these two are related. So, for example, if we have a hydronium ion concentration of 1 times 10 to the negative 3rd, molar. Okay, so that translates into 0.001 molar for a concentration. But really, this is how you're probably going to see it. But in your mind, if you can translate it into scientific notation, I want you to notice that a hydronium ion concentration of 10 to the negative 3rd corresponds to a pH of 3. So if you were to plug that into your calculator, pH equals the negative log of the hydronium ion concentration, which we're going to go 10 to the negative third, you would get pH equal to 3. Just for fun, let's do this for the concentration in pure water. So in pure water, we have a hydronium ion concentration of 10 to the negative 7th. To find the pH of that, pH equals negative log of 10 to the negative 7th. So our pH would be 7. So just take a moment, look at the chart here at the top, and notice that if our pH is less than 7, it's acidic. If our pH is greater than 7, it's basic. And notice how that corresponds to the hydronium ion concentrations at the top. That should fit in with what our last slide showed us, that the hydronium ion concentration, if it's greater than 10 to the negative 7, it's going to be acidic. If it's less than 10 to the negative 7th, it's going to be basic. Okay, so that's really easy when we have something 1 times 10 to the negative whatever. What if our hydronium ion concentration is not just 10 to the negative whatever? Let's say we get a hydronium ion concentration of 2 times 10 to the negative 5th. What's our pH now? Okay, now immediately I know you've already run to your calculators, you plugged in the number, you got the negative log, and you figured out what the pH is. Okay, what if we didn't always run to our calculators if we have a hydronium ion concentration? So we're looking at a solution that's 0.00002 molar. Okay, that's what you would see on a bottle. Not a very high concentration of hydronium ions. So I want you to think and take a moment to think through what this actually looks like back on the scale. So if it was 1 times 10 to the negative 5th, right, our pH would be 5. Now, where does this number fall on the scale? So that number is going to be somewhere between 10 to the negative 5th and 10 to the negative 4th. Okay, so let's just draw up another scale here. If we have something times 10 to the negative 4th, our pH would be 4. Okay, let's just estimate what our pH is before we calculate it. So somewhere between these two numbers, we have something like 2 times 10 to the negative 5th. We have, let's kind of just split it up, go over to 2, it doesn't matter. And let's just jump, it's logarithmic, right? Okay, so what's going to happen if we're going to estimate our pH? So here is the number we're looking at, 2 times 10 to the negative 5th. It's going to be somewhere between 4 and 5 on our pH scale. We can estimate it at, what, 4.7, 4.8 maybe? So always try to kind of estimate. That'll help you go faster rather than having to plug it into your calculator. And remember, the multiple choice section of the AP test, you cannot use a calculator. So you should be able to estimate these types of problems. You know, if our concentration is 8 times 10 to the negative 5th, we're going to look at a pH closer to 4.1, maybe 4.2. Okay, so if we actually plug this into our calculator, we get a pH equal to 4.7. Okay, so try to remember this. Try to keep this type of scale in mind, whether it's 10 to the negative fifth or whatever. Try to keep that in mind so you can estimate your pHs and move a little quicker. Let's do another one. What if our hydronium ion concentration is 8 times 10 to the negative 8th? Okay, what are we going to get for a pH value on that? Try to estimate it before you plug it into your calculator. Okay, so we have this 10 to the negative 8. So you're thinking in the range of pH of 8, right? But we have this 8 here, so it's going to fall somewhere between pH of 7 to pH 8. Because it's 8, we're getting much closer to this number actually being a negative 7. So we can estimate our pH in this situation as probably closer to 7. I would estimate 7.1, put it in your calculator, and oh, lo and behold, it's 7.1. So if you can think through this, and think through some examples now, it'll become secondhand for you to look at a number like this or concentration like this and say, wait, that's really close to 10 to the negative 7th, so my pH is going to be closer to 7.1. So really try to get used to estimating pHs before you plug them into your calculator. That will definitely help on the pH on the AP test. Okay, let's just ponder this thought for a moment. If we have a pH equal to 5, and let's say we add acid to the solution, and it increases to a pH of 3. Okay, increases acidity to pH 3, or decrease by pH 3. How big is the increase of the hydronium ion concentration? How much does the hydronium ion concentration increase by? What factor? Take a moment, think about that. Well, if the pH is 5, our hydronium ion concentration is 10 to the negative 5th. If our pH is 3, our hydronium ion concentration is 10 to the negative 3rd molar. What is this increase? That increased by a factor of okay, so don't just think because something has a pH of 3 and something has a pH of 4 that they're very closely related in their acidity. Okay, the further you're going apart on the pH scale of something, the bigger the factor is. So, you know, comparing something like soda to milk, you know, at like a 3-fold pH increase or decrease, really, the hydronium ion concentration increases by a factor of 1,000. So think about that next time you choose soda over milk. Okay, what if you're given a hydroxide ion concentration? What are you going to do? How are you going to find the pH? Okay, so there's a hydroxide ion concentration, 5 times 10 to the negative 10th. So how are we going to find the pH? That's right. We still remember that Kw equals the hydronium ion concentration times the hydroxide ion concentration. Which point we can plug that in. We know Kw, and we can solve for our hydronium ion concentration, and then find the negative log of that to find the pH of this solution. So let's do it. 10 to the negative 14 equals our hydronium ion concentration times our hydroxide ion concentration, which was 5 times 10 to the negative 10th. So our hydronium ion concentration equals 2, that's great, 2, times 10 to the negative 5th molar. Okay, try to estimate the pH before you actually calculate it. Okay, so we have 10 to the negative 5th, so it's going to be somewhere near 5. That number is greater than 1, so our pH is going to be between 4 and 5. So somewhere between 4 and 5. That's a fairly small number, so we can estimate our pH being closer to 5. So let's estimate at approximately 4.7 for our pH. So keep that in mind. Plug in a calculator, I think you get like 4.69. Sweet, close enough. So if you're given the hydroxide ion concentration, plug it into the Kw expression, solve for hydronium ion, and plug into pH. But wait, of course there's got to be an easier way. So here's our easier way. We know that for pure water, so pure water, pH equal to 7, hydronium ion concentration, I don't know what happened to that bracket, equals 10 to the negative 7th, which also equals our hydroxide ion concentration. So if they're both 10 to the negative 7, we can reason out that if we add our pH plus our POH, wait, POH, what's that? Can we think about this? POH is the negative log of our hydroxide ion concentration. If our hydroxide ion concentration is 10 to the negative 7th, we take the negative log of that. There should be a 7 there. There we go. We get our POH of 7. So we can easily reason out that pH plus POH equals 7. So if you're given a hydroxide ion concentration, you can plug it into the POH expression and find the power of the hydroxide ion concentration. And I think that's much easier to do. Wait, did I say that it equals 7? Oh my gosh, people. Oh my gosh. Try again. 14. That was close. I know, you guys were freaking out for a minute. So pH plus POH equals 14 because our POH equals 7, pH equals 7. Whew. But I'm pretty sure it's much easier to subtract from 14 than to find the negative log of one thing, put it in the equation, and find the negative log, so on and so forth. So know that that equation is handy for you. That's a good one to use. And here's a little infographic for you. You can go between all of these things. So you can go back and forth from hydronium ion to hydroxide ion. These are not equilibrium arrows. We can go back and forth arrows. So we can calculate back and forth between those two. What could we use here? Kw. From our hydronium ion concentration, we can go back and forth. Again, not equilibrium arrows, just kind of back and forth. we can go back and forth to our pH, and we would use negative log of our hydronium ion concentration. And now that we learned pH plus POH equals 14, not 7, 14, equals POH, we have pH plus POH. We can go back and forth between those numbers. 14. Oh, and let's finish our little square off. Not equilibrium arrows, back and forth arrows. We can use our negative log of our POH, or of our hydroxide ion concentration, to get POH. So keep this handy graphic in mind when you're doing all of these calculations for your strong acids and strong bases. Just one little example. One more. This is a good one. If our hydronium ion concentration equals 10 to the negative fourth, pH is going to be 4. Our hydroxide ion concentration in that situation is going to be 10 to the negative 10. Our POH is going to be 10. Add them together, you get 14. So if our hydroxide ion concentration is 10 to the negative 10th, our pH is 4, and life is good. A couple of examples. Calculate the pH of a 0.10 molar hydrochloric acid solution. This can only be done with strong acids and bases. Say that again. It's not a strong acid, not a strong base. You can't do it the way we've been working on in this video. Okay? Because of this. Hydrochloric acid in water dissociates 100%. There is no equilibrium. Okay? So all of our hydrochloric acid is going to make that hydronium ion. So we're going to get 0.1 molar of our hydronium ion. Okay, so it's going to dissociate 100%. Okay, so when it's all said and done, we're going to have 0.1 molar of that. We're also going to have 0.1 molar of this. Let's not forget about that, but in this situation, that's not important. So our hydronium ion concentration equals 0.10 molar. Put it into scientific notation in your mind. 10 times 10 to the negative, or 10 to the negative first, and our pH is going to be equal to 1. Okay, that was really easy. You guys can plug this into a calculator. Negative log of 10 to the negative first is our pH. Okay, another example. Calculate the pH of a 0.1 molar sodium hydroxide solution. Okay, that's a strong base. It's going to split apart 100% into its ions. So we're going to have sodium ions and hydroxide ions. So our 0.1 molar, our concentration of our hydroxide is going to be 0.1 molar. Now, in that situation, we can calculate the POH. So our POH is going to be the negative log of 0.1 molar. Which also is 10 to the negative first. So our POH is going to be 1, which is going to make our pH, so pH plus POH equals 14. Hopefully this is really easy math in your head. Our pH is going to be 13 in this situation.